Today we're going to talk about Chapter 6, Standard Deviation in the Normal Model. Rescale and data. Add and subtract in the same number to and from each data value. The distribution is shifted while the shape is unchanged. Measures of center, mean, median, Q1, etc. are shifted. Measures of spread, standard deviation, IQR, range, etc. are unchanged. Multiply and divide in each data value by the same number or factor. The distribution is stretched or compressed. Measures of center, mean, median, Q1, etc. are scaled by the factor. Measures of spread, standard deviation, IQR, range are scaled by the factor. Standardized values. Standardized values, or z-scores, are used to compare values from symmetric, unimodal data sets having different means and standard deviations. The z-score for data value y is z equals y minus y bar all over s. Standardized in all the data values shifts the mean of the data set to 0 and scales the standard deviation to a value of 1. If z equals 0, the data value is at the mean. If z is greater than 0, the data value is greater than the mean. And if z is less than 0, the data value is less than the mean. Example 1. If z equals 1, the data value is blank, the standard deviation, blank, the mean. So think about that and come up with your answer. So you should have one standard deviation above the mean. Example 2, if z is blank, the data value is 2.5 standard deviations below the mean. So take a moment and think about that one. You should have negative 2.5. In example 3, the mean weight for members of a female soccer team is 134.7 pounds and the standard deviation is 10.7 pounds. Calculate the z-score of a player who weighs 120 pounds. So z would be y minus y bar all over the standard deviation. And you should get negative 1.37. Another player's z-score is 2.83. How much does she weigh? So we would use the same formula, but the z-score would be 2.83. And we know it should be above the mean because that's above 0 equals y minus 134.7 all over 10.7. And you should get y equals 2.83 times 10.7 plus 134.7, and that equals about 165 pounds. So let's talk about data models. Real data sets and their distributions can be described using models. Models are never perfect descriptions of the data, but they can be very useful for analyzing and making predictions. A normal model can be used to describe symmetric, unimodal distributions. Mu is the mean of the normal model. Sigma is the standard deviation of the normal model. N with parentheses mu and sigma, so that stands for the normal model with its mean and standard deviation, indicates a normal model with mean mu and standard deviation sigma. Let's look at the 68, 95, 99.7 rule. This is something good to have memorized. So when we talk about this, your mu is at the center. So here would be my mu. And this is one standard deviation to the right. So this would be mu plus sigma. This is two standard deviations to the right. So this would be mu plus 2 sigma. And this is three standard deviations to the right. So this would be mu plus 3 sigma. Going in the opposite direction, this is one standard deviation to the left. So this would be mu minus sigma. This is two standard deviations to the left. This would be mu minus 2 sigma. And this is three standard deviations to the left. And this would be mu minus 3 sigma. Now, from mu minus sigma to mu plus sigma, that's about 68% of the data. Values fall within one standard deviation of the mean. Within two standard deviations of the mean, that would be 95% of the data. And we'll go ahead and write it up here. So 95% of the data falls within two standard deviations of the mean. And then within three standard deviations of the mean, you have 99.7% of the data falls within three standard deviations of the mean. And when we use the standard normal model with 0 and 1, that's when it's in terms of your z-scores. With 0, 1 standard deviation, 2 and 3, -1, -2, -3. And here, the 68, 95, 99.7 rule still applies. Let's go ahead and look at some examples. Calculate the area under the standard normal model using the calculator's normal CDF function. Use -1 E99 and 1 E99 for negative infinity, infinity, respectively. Always draw a diagram of the normal model when making these calculations. This is how you show your work. So we're going to go ahead and do example 4 together. Find the percentage of data values that are less than 1.5 standard deviations above the mean. So first, let's go ahead and draw a picture of this. So you draw your normal curve. Here we have mu. And we can draw three standard deviations in. 1.5, this is 1 to the right, so 1.5 would be in the middle. So that would give me a value of 1.5. And they said less than, so it would be this entire area here. So our z equals 1.5. And remember, you were told how to find z in the previous examples. So you would put in your calculator normal CDF. And to find that, that's under the distribution key. And you would have -1E99. To get the E key, that double E, you press the second, and I think it's above the 7 or the comma, and there's a double E there. And if you can't find it, I'll show you in class. To 1.5. And you can end there, but you could always put the mean and the standard deviation, which is 0 and 1. If it's asking you for that, you might want to do that because some of the calculators do that. And you should get about an area of 0.933. So your answer would be 99.3% of the data is less than 1.5 standard deviations above the mean. Let's go ahead and look at example 5. Find the percent of data values that are more than 0.7 standard deviations above the mean. So again, we draw our normal curve. Here's mu. 0.7 would be right about here. That would be this entire area. So this would be normal CDF of 0.7, 1E99, 0, 1. And that would give me about 0.242. So 24.2% of the data is 0.7 standard deviations above the mean. Let's go ahead and look at example 6. Find the percentage of data values that are less than 1.3 standard deviations above the mean. Again, we need to show a picture so that we understand what it means. (1.3) standard deviations from the mean, and it's less than. So 1.3 to the left would be about here, so that's negative 1.3, and 1.3 to the right would be about there. So we're finding the area between the 2 points. So this would be normal CDF of negative 1.3 to 1.3, 0, and then 1, and we get about 0.806. So 80.6% of the data is within 1.3 standard deviations of the mean. Let's look at example 7. We're going to calculate the z-score for a given area under the standard normal model. Use an inverse norm. So again, that is in the distribution key. Again, always draw the normal model to show your work. Okay, so example 7, what z-score cuts off the lower 35% of the data values? So here I have mu, and it's the lower 35%. So I would go ahead, draw a picture. And what we're saying is this area in here is 35%. And we need to find this z. So our z would equal inverse norm of 0.35. And you would get about negative 0.39. So z equals negative 0.39. Example 8, what z-score cuts off the upper 30% of the data values? So mu. So I'm looking for this z. And this would be the upper 30%. Okay, so one thing we talked about with our calculator for inverse norm, you can only find the area to the left. You can't find the area to the right. So when we do this, our z-score would be inverse norm 0.7 because 1 minus that 0.3. And you would get 0.52. So z equals 0.52. Then let's go ahead and look at example 9. The mean of a normal distribution is about 262, and 14% of the data values are above 300. What is the standard deviation of this distribution? So let's go ahead and draw a picture. Let's see if I can make a better curve. Okay, so the center is 262, and I was told I have 300 here. It says the area of these data values is 14%, which would make the area of this side 86%. So I need to find my z-score of 300. Z would be inverse norm of 0.86, which equals 1.08. And then using our formula for z is y minus y bar all over my standard deviation to find my standard deviation. So I'd have 1.08 equals my y, which is 300, minus my mean, which is 262, all over sigma. I go ahead and I solve for that, and I would get sigma equals 35.2. So my standard deviation is 35.2. Cumulative distribution function. So an ogive. The area under the probability density function, so these are also known as probability density functions between two values, is proportional, so PDF is what you would know that as, is proportional to the probability that an arbitrary chosen data value falls in that interval. The cumulative distribution function gives the proportion or percentage of data values that fall below a specified value, probably that an arbitrary chosen data value is less than a specified value. So a probability density function, the normal one, would look like a normal curve. And let's see if we can get it with 0 here. However, a cumulative distribution function would look like this. And with a cumulative distribution function, %100 of the data values are at the top, 3/4 of the way is 75%, halfway is 50%, and then 25%. Notice that this splits it up into 4s. Down here, you would have your min, and up here, your last value would be your max. So at 25%, that would be Q1, Going out to 50% would be Q3, and going out from 75% would be our Q2 and then Q3. And Q2 is also your median. Normal probability plot. A normal probability plot graphs actual data values against the expected normal z-scores for each data value. If the plot is relatively linear, then the normal model is appropriate for describing the data. So here I have example A and example B. Example A is relatively linear, so the normal model would be appropriate for describing this data. However, example B is not relatively linear, so the normal model would not be appropriate. The 68, 95, 90, 90.7 rule would be appropriate to use with the data in example A because the normal probability plot is linear.